In this video, we discuss Fourier Sine series. This is based on section 2.2 of solution techniques for elementary partial differential equations, second edition by Christian Constanda. We're going to start our discussion with a review of the full Fourier series, which we discussed in the last video. Then we'll talk about even and odd functions and some of their properties as related to integrals. And then we'll work through an example where we find the Fourier sine series for a particular function. Remember last time, we said if we start with a function f defined on the interval from negative L to L, if we want to, we can construct what's called a periodic extension of f to the entire real line. And the way we do that is we ignore this value of f at the left endpoint, and then we just draw that. And then we ignore it again, and then we draw that again, and we draw that again, over and over again, from negative infinity to infinity. If we do that, what we've created is a function that is periodic with period 2L. That means if I find f of x plus 2L, that's going to be the same as f of x for all x in the reals. More specifically, let's remember what this is. If I go to a particular x value and I find the y value there, this is saying if I add 2L to that x value and I find the y value, I'm going to get the same y value. And if I add 2L to that x value and I find the y value, I'll have the same y value. Or if I subtract 2L from that x value, I'll find the same y value. And it turns out you can add and subtract 2L as many times as you want. So rather than stating this, we often state this. F of x is equal to f of x plus 2L times n, where n is any integer. N is the number of times we're adding or subtracting 2L from that x value. And this is saying if you do that, you're going to get the same y value that you had when you started. Now, if we have a function that we have constructed like this, we've turned the function from the a function on the interval from negative L to L to a periodic function with a period of 2L. It makes sense to think of expanding that function in a series that looks like this. So this is saying, let's take a combination of cosine and sine functions, where those cosine and sine functions have different frequencies. And let's think about what combination is necessary so that when I add all these cosine functions to all of these sine functions and I add that to a constant, under some conditions, I actually get that function f that I started with back, or something that's very similar to f, or very similar to that periodic extension of f to the real line. Now, all of this is going to make a lot more sense when we think of it in terms of these building blocks. Now, I'm not going to go through the building blocks for the sine functions, but they're very similar to the cosine functions. So let's say we're starting with a y equals cosine of n pi x over L. Now, n is a number that's changing. We're going to have n equals 1, 2, 3, 4, 5. We're going to have n equals 100, 1,000, all of that in here. From n equals 1 to infinity, we're going to have that many cosine functions, countably infinite cosine functions. Now, in the last video, we showed that the period of one of these guys is 2L divided by n, and that we'll see n cycles of that function over the interval from negative L to L. Now, I can write that down, and a lot of students can do the calculations that lead to that, but it's really much more intuitive when we look at it for specific values of n. So let's look at what we get when n equals 1. We've got cosine of pi x over L. This is a function with a period of 2L. And you're going to see one cosine wave or one cycle on the interval from negative L to L. So when n equals 1, we get one cosine wave on that interval. Now, most of the time when we draw a cosine function, at least if we were in a trig class, we would draw it on the interval from 0 to 2 pi. Or if the period was 2L, we would draw it on the interval from 0 to 2L. So we'd start over here at 1, then a fourth of the period later at L over 2, we get 0. Then a fourth of the period later at L, we would get -1, then we go back to 0, and then we go back up to that maximum value. And that would be our cosine wave. And this continues all the way to negative infinity and all the way to positive infinity in both directions. So I could repeat that pattern over here. We've got 0 here. At negative L, we'll get -1, then we'll have 0, and then we'll be back up at our maximum value of 1. And we'll see that. Now, for our purposes, when we're thinking about Fourier series, we don't tend to think about this interval from 0 to 2L. Instead, we think about this interval that's symmetric about the origin. So rather than looking at the interval from 0 to 2L, we choose to look at the interval from -L to L. So this is our cosine of pi x over L. And we're going to focus on that part between -L and L. That's right there. Now, when n equals 2, we'll have cosine of 2 pi x over L. Now, this function has a period of 2L divided by n, or 2L divided by 2, which is L. So this repeats itself every L units in the x direction. And if it repeats itself every L units, and we're going from -L to L, then we're going to see 2 cycles of this function on the interval from -L to L. So this will look something like this. On the interval from -L to 0, I'll see that cosine wave. And on the interval from 0 to L, I'll see a different cosine wave. And of course, you would continue in this way from -infinity to infinity. I could keep drawing. But we're not really interested in the whole thing. Again, we're only interested in the part between -L and L. So I almost want to just shade all the rest, the part that we're not interested in for right now. Say, let's not look behind this line. That's not our interest. It's not that it's not there, it's still there. It's just not of particular interest to us. So we're ignoring that. We're ignoring this. But our red function, we see 1 period of cosine of pi x over L in the interval from -L to L. And for n equals 2, we see 2 periods for cosine of 2 pi x over L on the interval from -L to L. And then if n is equal to 3, as you can imagine, we've got cosine of 3 pi x over L. And so that's taking our interval from -L to L, our period of 2L, and it's dividing it by 3. So basically, I'm going to have 3 of those cosine waves over the interval from -L to L. And I'm focused on the interval from -L to L because that's where we're interested in this infinite series giving us that function f back. Because f was defined on the interval from -L to L. Once I construct a series that looks like this, I'm interested in where that converges on the interval from -L to L and how the function that this converges to relates to the function that I started with. So I'll have 3 periods here. So I'll try to split this into thirds. And you just do the best you can. And so that is my cosine wave where you've got 3 of them. Now, remember what this is. That's just a constant times the first one, the red function, plus a constant times the second function, the purple function, plus a constant times a third. And you're going to have infinitely many terms like that. And you're going to have infinitely many terms that look like this for sine functions. And you're going to add all of those together and you're going to add them to this constant 1/2 of a naught. And our goal is hopefully to get f back or something that's really closely related to f. So that's dealing with the convergence of this series to a function. And we talked about that in the last video as well. So we said if f is piecewise smooth, then the series that we are constructing will converge to f. It's going to give us exactly what we want when f is continuous. Or it's actually, let's say, when the periodic extension of f is continuous. And then when the periodic extension of f has a jump discontinuity, and it's possible f will have a finite number of jump discontinuities if f is piecewise smooth. That's part of the definition of piecewise smooth. Then what you do is you take the average of the limit of f as x approaches x naught from the left, and the limit of f as x approaches x naught from the right. This is provided that we've got we've got a jump discontinuity at x equals x naught. You take those, you add them together, and then you divide by 2. So I'm going to say at jump discontinuities, x equals x naught. That's what the series converges to. So Fourier series, a full Fourier series, is a weighted average of these sinusoidal functions, each n giving us a wave of a different frequency. And then we're saying, what exactly is the right recipe? Or what exactly is the right combination of these waves and the corresponding, or in the similar waves for the sine functions? What combination do I need to have so that if f is piecewise smooth, when I add these together and I add this together, I get the function f back when f is piecewise, or when the periodic extension is continuous, or I just get the average of the limits from the left and the right at every jump discontinuity. So you might be saying to yourself, well, what is a Fourier sine series then? Well, sometimes if f has certain symmetry, this whole series reduces to just a sine series. So it turns out sine is an odd function. If f is an odd function, then we just look for an expansion in terms of odd functions. If f is an even function, well then we don't really need any contributions from odd functions. We would just take combinations of even functions to get an even function f back. So that's kind of the overview. But let's talk about even and odd functions first. And then we will talk about the Fourier sine series, and then we'll do an example. You guys probably are already familiar with even and odd functions. Probably seen it in a pre-calculus class. We say that f is even if f of x is equal to f of negative x. Now it's helpful to look at a picture of an even function when we think about this. So here's y equals x squared. That's an even function. Now, what do these symbols mean? Well, if you go x units in this direction and you find the y value, that y value is f of x. If we go x units in the opposite direction and we find the y value, that y value is f of negative x. Now, if I did a better job drawing my picture, these two y values would be exactly the same for an even function. If f of x and f of negative x, those two y values are the same as each other, we say that this is an even function. Now, if we go x units in this direction, find our y value, we go x units in this direction on the graph of y equals negative, or the y equals x squared, and we find our y value. We get x squared on this side, we get negative x squared on this side, we're gonna have the same y value. So if I use, let's say x equals 2, if I plug in 2, I get 2 squared, which is 4. If I substitute in -2 times -2 is also 4. So this is an even function. Other examples of even functions. Any polynomial whose terms have only even degrees is an even function. I said polynomials, I guess I should say, with terms of only even degrees are even functions. So I think it's kind of obvious that y equals x squared is even. Of course, y equals x to the 4th is even. Y equals x to the 100th is even. But this is also saying that if you take 1/5 of x to the 100th, then you subtract 7 times x to the 52nd, and then you add 3 times x squared, because that term is even and that term is even and that term is even. All of those have even exponents. This polynomial is an even function too. So if I go x units from the origin to the right, and I go x units from the origin to the left, and I find the y values are going to be exactly the same, as long as all of the terms have even degrees. It says polynomials with terms of even degrees only, or only even degrees, are even functions. Other examples, cosine. Y equals cosine of x, and the case that we're looking at for our Fourier series, cosine of n pi x over L, also even. So let's say we're looking at y equals cosine of pi x over L. So we're on the interval from negative L to L, and we've got a graph that looks roughly like this. And of course, that pattern continues in both directions. We say that this function is an even function because if we go x units in this direction and find the y value and the same number of units in the x direction, we go x units to the right or x units to the left, and we find the y values are the same. So this is an even function. Now, I'm used to doing this with cosine. With cosine of x, we could go over here to pi over 2, find cosine of, let's do pi over 4. We could do cosine of pi over 4. We would get square root of 2 over 2. If we go to cosine of negative pi over 4, we would get negative square root of 2 over 2. Or excuse me, positive square root of 2 over 2. They're going to be exactly the same y values. So cosine is even, and so is this cosine function here. I guess I probably should have used the picture of just cosine of x. It's going to look very similar. Made it a little wider this time, but you get the idea. This is y equals cosine of x, and that one's y equals cosine of pi x over L. But if I go to pi over 4 and I find the y value, I get square root of 2 over 2. If I go to negative pi over 4 and I find the y value, I get square root of 2 over 2. So cosine of x and cosine of negative x are the same. So that's what makes it even. And it turns out to be true for cosine of n pi x over L as well. So if I go to cosine of n pi x over L, and then I go to cosine of negative n pi x over L, so I'm just replacing x with negative x, those y values are the same. So that's what makes a function even. Now, if we're on a symmetric integral or interval about the origin, so let's say I wanted like an area under the curve from say here to here, from negative a to a. And I wanted this area under the curve between my curve and my x-axis. Well, it turns out that I don't have to do that calculation every time. I don't have to evaluate the integral from negative a to a of my function. I can actually use a shortcut if my function is even. Because of the symmetry, the sort of net area, the area between the function and the x-axis, let's say we went out over here. Maybe this is our a. Not use that one. Maybe this is our a. So I'm looking at this area versus that area over here. Now remember, when we evaluate the integral from a to b of f of x dx, what we find is the area between the function and the x-axis. What we get is that area minus the area between the function and the x-axis that's below the x-axis. So we get the area above minus the area below. Of course, that's still true for even functions. It's true for even functions, odd functions, functions that are neither. But we see that if we are talking about an even function, this net area on this side, let's say from 0 to a, we'll take this area minus this area. That's going to be exactly the same as that area minus that area. So we can say the following. If f is even, then rather than evaluating the integral from negative a to a of f of x, we can take a small shortcut. We can evaluate the integral from 0 to a and then just double it. That will be helpful for us whenever we have an even function that's perfectly legal. Now, if our function is odd, we see a different kind of symmetry. I think the easiest example we have of an odd function is y equals x cubed. So it's going to look something like this. Here, when you have an odd function, if you go x units in this direction and find the y value, and x units in the opposite direction from the origin and find the y value, and then you compare those two y values, one's called f of x and the other one's called f of negative x. The y values are not the same, but they're opposites of each other. So if I go to x equals 2, I get 8. If I go to x equals negative 2 for this function, I get negative 8. If I go to x equals 1, I get 1 cubed, which is 1. If I go to x equals negative 1, I get negative 1 cubed, which is negative 1. So the y values are the same in magnitude, but with opposite signs. So you can put an equal sign here as long as you multiply one of these guys by negative 1. I'll put the negative over there. So we'll say that f is odd if this holds. So I want f of x and f of negative x to be opposites of each other. And we'll have that right there. Now y equals x cubed is obviously an odd function. And as you can imagine, y equals x to the n is an odd function as long as n is odd. So if I put an odd number, or excuse me, if I put any number in here and I raise it to an odd power, if that number is positive, I'm going to get one result. If that number is negative, because the negatives cancel in pairs, I'm still going to have the same result as before, but with an extra negative that doesn't cancel out. So odd functions include polynomials with terms of only odd degrees. Those are going to be odd functions. So y equals x cubed, y equals x to the 5th, y equals x to the 7th. But also if we can take combinations of those, so y equals negative 1 over 1,000 times x to the 15th plus 26 x to the 5th minus x cubed plus 17x. Now this is an x to the 15th, the 5th, the 3rd, and the 1st is implied there. All of those powers are odd, so this is an odd function. Notice over here, these are even. I could even add a constant here. If I put a 4 on there, you can think of that as being multiplied by x to the 0. So this is even. X to the 0 would also be an even term. So if we have a polynomial with only even terms, it's an even function. If we have a polynomial with only odd terms, it's an odd function, or it's actually terms of odd degrees is what I should say. But for our purposes, we're also really interested in these two functions, sine and cosine. Cosine was an even function. Turns out that sine is an odd function, and so is sine of n pi x over L. So let's look at that sine function again. Now that repeats every 2 pi. We tend to look at it like that. This is y equals sine of x. If I go x units in this direction and find the y value, and x units in this direction and find the y value, the y values have opposite SIGN signs. So sine of x and sine of negative x are the same, except one of them is multiplied by -1. So if I go to, let's say pi over 4, or let's say pi over 2, I find the y value, I get 1. If I go to negative pi over 2, sine of negative pi over 2 is -1. That's true. Now sine of n pi x over L is similar. Let's use n equals 1. So we'll have pi x over L. This is a function with period 2L. It's going to look like that familiar sine wave, except instead of repeating every 2 pi, it repeats every 2L. So negative L there, 0, L, 2L, and so on. And we keep going. And again, remember, whenever we're looking at Fourier series, we're not really interested in the whole thing, even though that's part of our construction. When we look at the periodic extension of our function f, we tend to be interested in these functions, sine and cosine of n pi x over L, on the interval from negative L to L. So rather than looking at this 0 to 2L interval, we're going to focus on that negative L to L interval. Now, if I find the area under these curves from, say, negative a to a, the area above the x-axis on this side is matched by area below the x-axis on the opposite side. Because that happens, whenever we take the integral of an odd function over a symmetric interval like negative a to a, we always get 0. So we'll say if f is odd, then the interval from negative a to a, or the integral from negative a to a of f of x is equal to 0. Now we could prove all of these identities algebraically if we wanted to, using the fact that negative f of x is equal to f of negative x for odd functions, and that f of x and f of negative x are equal to each other for even functions. We could do that if we wanted to. And that is done in the Constanda partial differential equations textbook. But I think thinking of it visually is more intuitive. I think we can all see that that area is going to be matched by that area, and they're going to cancel out when we evaluate this integral, which gives us area above the x-axis minus area below, and we'll get 0. Okay, so we know about even and odd functions. We know their corresponding identities. We know that if f is even, then instead of evaluating this integral, we can just evaluate that integral and double it. If f is odd, we know that if that interval that we're integrating over is symmetric, we get 0. That's very nice. I won't prove this here, but I think it's pretty obvious. You can use the these identities that we just talked about, this one and this one, to prove this. But if you have an even function times an even function, so this is a function for which f of x and f of negative x are the same, and the same is true there. If you multiply those two functions together, you'll have an even function. If you take an even function and an odd function and you multiply them together, the result will be odd. And of course, we could multiply in any order we want. So we'll still get an odd function. And this one is a little surprising or counterintuitive, but an odd function times an odd function turns out to be an even function as well. So if one is odd and the other is even, you get an odd result. If they are the same, if they're both even or they're both odd, you get an even result. We can use these facts together with the procedures and the process that we use to come up with the coefficients of the full Fourier series to infer what would happen if f is odd, or what would happen to our series expansion if f is even. So that's sort of the next question as we think about the Fourier sine series. Let's consider a function f. You've got an odd function f. What does the Fourier series look like? Now, there are a few things that we ought to remember before we do that. So let's say, just as a formality, that f of x is equal to its series. That's always what we assume when we find the a sub 0, the a sub n, for n equals 1 through infinity, and the b sub n. We assumed those were equal, and then we had some identities that we talked about last time. We said, if you take the integral of cosine of n pi x over L over the interval from negative L to L, you get 0. And it turns out that if you do the same thing with the sine functions, you also get 0. And then we said, not only that, but if I take cosine of n pi x over L and multiply it by cosine of m pi x over L and integrate from negative L to L, I'm going to get 0 most of the time. As long as n and m are not the same, I'll get 0. But if n and m are the same, it turns out that we get L. And the same is true if those were sine functions multiplying each other. So if I had sine of n pi x over L and sine of m pi x over L, and we integrate from negative L to L, we're going to get 0 most of the time, except for when those angles are the same. In that case, we get L. And then we said, if we take a cosine and a sine and we multiply them together and we integrate from negative L to L, we always get 0. So we had these 5 identities that we used. And then we assumed that these were equal to each other. And then what we did was we integrated this from negative L to L. We multiplied by sine of m pi x over L to get the b sub n's. We multiplied by cosine of m pi x over L and integrated from negative L to L to get the a sub n's. But that was our process last time. And I think I'll just write this down for you and then we'll talk through it. This is what we talked about in the last video. We said if we want to find that 1/2 a naught, we want to find that a sub 0 a naught, we just integrate this whole thing. We assume that the left-hand side equals the right-hand side, and we integrate from negative L to L. On the left-hand side, we get the integral from negative L to L of f of x. And on the right-hand side, we ended up with this constant integrated from negative L to L. So that's just a constant, like the y value is that constant. Like that's how high our little rectangle would be. The width of our rectangle would be 2L. So we just end up with that times 2L. So we just get L times a naught there. But if we integrate this piece from negative L to L and this piece from negative L to L, because of these two identities, we get 0. And we talked about area and how that relates to these identities in the last video. So what happened was after we integrate everything from negative L to L, these guys are gone and these guys are gone. This ends up being 1/2 a naught times x evaluated from negative L to L. On the left-hand side, you get this. And so this ends up being 1/2 times a naught times 2L. 1/2 and 2 reduce, and we just end up with a naught L. So we get a naught is 1 over L times this integral from negative L to L of f of x. That's still true. But if f is odd, that's the integral of an odd function over a symmetric interval. So that's going to be 0. So this is the formula we came up with last time. But because we're integrating from negative L to L, it's the same as integrating from negative a to a. If f is odd, we get 0. Now, to find the a sub n, we multiply by cosine of m pi x over L, and we integrated from negative L to L. Now that's a constant. I'm just looking at the left-hand side. I've got a constant times the integral from negative L to L of this. Well, that's going to be 0. And then if I take this cosine and I multiply it by the sine functions and I integrate from negative L to L, well, I've got infinitely many of those, but that's going to look like these guys, a cosine times a sine, and I'm integrating from negative L to L. So those will be gone. And then here, if I multiply this by cosine of m pi x over L, and I integrate from negative L to L, I'm going to get 0 most of the time, except for when n and m are equal to each other. Then I'll get L. So what'll happen on the left-hand side is this piece times that integrated from negative L to L is going to give me a 0. That piece times that integrated from negative L to L will be 0. And this will end up being a sub m, because we're only going to have one of those. All of them are going to reduce except for the one where n is equal to m, times L, because that's what we get right there. So the left-hand side is a sub m times L. And the left-hand side is the integral from negative L to L of f of x times cosine of m pi x over L. So I can change from n or m back to n, and I have this. And that is still our formula. I know I'm doing a lot of hand waving here. If you want to see me write out all of this stuff, I did that in the last video. But you might say to yourself, okay, well, what happens if f is odd? Well, if f is odd, this is an odd times an even. Remember, cosine is even. An odd times an even is odd. So this is the integral of an odd function over a symmetric integral. So we're going to get 0. So those are all going to be 0 if f is odd. Okay, and then you might say, well, these are 0 and those are 0. Well, what about the b sub n? If we multiply all of these guys by sine of m pi x over L and integrate from negative L to L, what happens? Well, the constant times this, integrated from negative L to L, will be a constant times this 0. So that piece will be gone. When I take these cosine expressions and I multiply by the signs and integrate from negative L to L because of this guy, those will be gone. The only ones that won't be gone are these signs, or the b sub n times the sine. So let's do that. We have the integral from negative L to L of f of x times the sine of m pi x over L equals the sum as n goes from 1 to infinity of b sub n times the integral from negative L to L of sine of n pi x over L, that was there, times sine of m pi x over L. And everything else is zeroed out. But this guy, that integral is 0 when the angles are different, and that integral will equal L when the angles are the same. So what we have is b sub m on this side times L equals the integral from negative L to L of f of x times sine of m pi x over L dx. So b sub n is 1 over L times the integral from negative L to L of this. Now, if f is odd, this is an odd times an odd times an odd would be even. So we could actually do that instead. And use that as our formula for b sub n, because of the symmetry. So these are gone and these are gone because f is odd. And so we are going to expand f as a sum of a series of odd functions. So we're going to have infinitely many odd functions, and we're going to say, well, what's the appropriate weight? So I've got some of those odd functions, I've got 2 of these and a half of that and, a quarter of that, and I add them all together and I get f back. Like, what do those b sub n's need to be? What do those weights need to be so that when I add those odd functions together, I get the odd function that I started with? So the sine series for f of x looks like this. And everything that we said about convergence before still holds. So these will converge, this will converge to the periodic extension of f, where the periodic extension of f is continuous. But we really should be looking at, more detail. So let's look at a little bit more detail on the next page. So f will be expanded in this way, or the b sub n are given by those formulas. Okay, now this only makes sense if f is odd, or if you just have a function defined on an interval from 0 to L, you can make it odd. So let's say we're given a function f, and f is defined on 0 to L. Maybe our function looks like this. Now, if I want to create an odd extension of this, I want the y values when x is equal to negative x to be the opposite of the y values on this side. So if this y value is 1/2, I want this y value to be negative 1/2. If this y value is 1, I want this y value to be negative 1, and so on. And so this would be my odd extension of f. And then we could draw that multiple times for periodic extension. don't know, something about that doesn't look appealing to me. I'm going to make a different function. I don't like the look of that graph. Let's make one that looks like this. Here's my odd extension. So the way we come up with the odd extension is like this. We're going to require f of negative x and f of x to be opposites of each other. And then at the origin, we're going to require f of 0 to be 0. So we'll have an open circle there and we'll draw that. And then on the other side, we'll have an open circle there and we'll draw that. And that will be the odd extension of f to the interval from negative L to L. Now, if I draw that multiple times, actually, you're thinking about infinitely many times. So it should be open. Then you get the odd extension to the entire real line. So this is the periodic extension of the odd extension of f. Now, because the resulting function is an odd function, it makes sense that we would expand it in terms of odd functions. And again, if you want to prove it to yourself why that's true, not just why it's intuitively true that if f is odd, you'd expect it to be made up of odd functions. You can do some of the algebra and you can see why the a sub 0 and the a sub n would have to be 0 so that we don't have any contributions from even functions if we're trying to get an odd function. So I take my f that's defined on 0 to L and I create the odd extension and then the periodic extension of the odd extension of f, then I can come up with the Fourier sine series for this one that I started with. So here's our example. We're asked to construct the Fourier sine series for the given function f and discuss the convergence of this series on the interval from 0 to L where f is defined and sketch the function to which the series converges pointwise on the interval from negative 3L to L. So first, I've got my function f here. I think it makes sense to sketch f just to start. So f is equal to x on the interval from 0 to 1. So we've got that. And f is equal to negative 2 on the interval from 1 to 2, of course, not including 1. So that's f. Since this is defined on the interval from 0 to 2, that tells me that my L is equal to 2. So if I want to construct the odd extension of f now, and we're going from 0 to 2 to negative 2 to 2. We'll have the following. On the interval from 0 to 1, we still get x, that's 1. And on the interval from 1 to 2, we get -2. But we want f of x and f of -x to be opposites of each other. So when I come over here to -1, if I go over here to x equals 1, I get +1. If I go over here to x equals -1, I want the opposite of that. I want -1. So we're going to see this on this side. Now, on the interval from 1 to 2, f of x is -2. That means on the interval from -1 to -2, I want my y values to be opposite of that -2, which makes that +2. You see how it's an odd extension? If I go x units in this direction to find the y value and x units in this direction and find the y value, they're opposites to each other. If I go out here to, let's say, x equals 1.5, the y value is -2. If I go to x equals -1.5, I find the x value or the y value is +2. So the y's are opposites. That's my odd extension of f. Now, I want a periodic extension of the odd extension. I want to draw that next. That is very closely related to the function that the series will converge to. And it looks like we want to sketch that periodic extension on the interval from -3L to 3L. So that's going to be the interval from -6 to 6. Now the periodic extension and the function the series converges to, those are not exactly the same. They're very closely related though. We'll do the best we can. I mean, you could use graph paper if you wanted to. You can make a perfect graph on graph paper. Nearly perfect. We're just trying to get a visual though, of what's happening. And okay, so let's first draw that odd extension on -2 to 2, but we're going to leave off that left endpoint to come up with a periodic extension. So from -2 to -1, we want the y values to be +2. I'm going to leave off the left endpoint. And then from -1 to 1, we've got y equals x basically. And then from 1 to 2, we get something that looks like this. Now you want that pattern to repeat over and over again. So on the next interval, we'll see this. Oops, that should be from 2 to 3. And then between 3 and 5, we'll see this. And then we will see this guy again. All right, now down here, we'll have this. Then from -5 to -3, we'll see this line segment guy again. And then from -6 to -5, we'll see this. Okay, so that is the periodic extension of the odd extension of f to the entire real line. Okay, so now we want to expand f in a sine series. And it's relatively easy to do. And we already know that L is equal to 2 because we are looking at the interval from 0 to 2. So I could substitute that in. To find the b sub n, we're going to do the same thing that we did before. We will multiply this equation, and we're thinking of it as an equation, by sine of m pi x over L, or m pi x over 2. And then we'll integrate from negative L to L. Or in our case, we're integrating from negative 2 to 2. So on the left-hand side, we'll have the integral from negative 2 to 2 of f of x, times sine of m pi x over 2 equals the sum, as n goes from 1 to infinity, of b sub n times the integral from negative 2 to 2 of sine of n pi x over 2 times sine of m pi x over 2. You got the two sine functions. This is going to be 0 most of the time, but it'll be equal to L, which in this case is 2, when the angles are identical. So what we'll end up with is this, b sub m multiplied by 2 is equal to the integral from negative 2 to 2 of f of x times sine of m pi x over 2. Of course, we could change from n or m back to n, as we often do. And then we have this. Now remember, f is an odd function. This is an odd function times an odd function, which gives us an even function. And the integral of an even function over a symmetric interval is 2 times that integral. But instead of going from negative 2 to 2, we're just going to go from 0 to 2. This part comes from the fact that we have the integral over a symmetric interval of an even function. And that 1/2 is the 1/2 from over there. That's the L that was multiplying the b sub m on that side. So 1/2 and the 2, of course, reduced to 1. And we end up with the integral from 0 to 2 of f times sine of m pi x over 2. Now, f was defined on 2 different intervals. It was defined on the interval from 0 to 1 to be x. And then on the interval from 1 to 2, f was equal to negative 2. So I guess I need n's there because I switched from m back to n. I know this is messy. Okay, so we're going to evaluate that, and we're going to evaluate that. Since I have a polynomial times a trig function, I will use tabular integration by parts. My u is my polynomial, dv is everything else. Sort of ignore that dx. I'll put it in parentheses at first, but we'll ignore that. In this column, we'll differentiate until we get 0. In this column, we'll anti-differentiate until both columns have the same number of rows. Antiderivative of sine is negative cosine. Since there's a number multiplying our x, we've got to divide by that number. Dividing by n pi over 2 is the same as multiplying by 2 over n pi. The antiderivative of cosine is sine. And we'll divide by n pi over 2, which is multiplying by 2 over n pi. So we end up with 4 over n squared pi squared. And don't forget the SIGN signs out front. Then the antiderivative of this function is this times this times positive 1 plus this times negative 1. So we'll have a negative 1 times a negative 4 and make that a positive 4. We're evaluating all of this from 0 to 1. Now over here, bring the negative 2 down, that's just a constant. And the antiderivative of sine is a negative cosine. Negative times that negative is going to make that a positive. And of course, dividing by, or because we have a constant multiplying our x, we're going to divide by that constant. Dividing by n pi over 2 is the same as multiplying by 2 over n pi. We evaluate from 1 to 2. Okay, so at x equals 1, we get negative 2 over n pi times cosine of n pi over 2. And over here, we'll have 4 over n squared pi squared. When x equals 1, that'll be sine of n pi over 2. Then we'll evaluate all of this when x equals 0. We get 0 times something, which is clearly 0, and then sine of 0 is 0. So we'll get 0 for that. Over here, we'll have 4 over n pi times cosine of n pi when x equals 2. And then we'll subtract what we get when we plug in x equals 1. So I'll have minus 4 over n pi cosine of n pi over 2. Okay, so now we just need to think about what cosine of n pi over 2 would be, and what sine of n pi over 2 might be, and what sine of n pi or cosine of n pi might be. Now, this is my regular sine wave, just y equals sine of x. Now, if n is an integer, when n equals 0, we'll get 0. When n equals 1, we'll have pi over 2 for that angle. When n equals 2, we'll get 0. So this is actually going from 0 to 1 to 0 to negative 1 to 0 as the angle changes by pi over 2 radians every time. So I think I might just leave it alone. We could say that it's going to alternate. It'll alternate between 1 and negative 1 whenever n is an odd number, and then it's going to be even whenever, or it's going to, when n is even, we'll get 0 here. Maybe I'll write that down for right now. This will be 0 when n is even, and then it'll be well, it'll be plus or minus 1 when n is odd, and we would need to think through a little bit more, like the consequences of that, and exactly how that sign, SIGN sign, relates to that odd number that we would get over here. Now, regarding cosine of n pi over 2, remember cosine looks like this. Cosine of pi over 2, or if cosine of 0 is 1, cosine of pi over 2 is 0, then we get negative 1, then we get 0, then we get 1. So we're going to have that same situation happening here, but whenever n is even, we'll get plus or minus 1 here. And we'll get 0 when n is odd. And as far as multiples of pi are concerned, That's cosine of 0, cosine of pi, cosine of 2 pi, cosine of 3 pi, cosine of 4 pi. That's going from 1, negative 1, 1, negative 1, 1, negative 1. So that's going to be negative 1 to the n. When n is even, we get positive 1. When n is odd, we get negative 1. So let's think through this a little bit more. We'll keep combining this with this. I've got negative 2 of those minus 4 of those. It's going to be negative 6 of those. And I've got 4 of these sine functions multiplied, or 4 over the n squared pi squared times the sine functions. Now I was trying to think of how I could come up with a pattern for these guys. I think we probably could in terms of negative 1 to the n. But we'd have to be pretty clever. It really depends on what that n is, modulo 4. And maybe that's beyond the scope of a partial differential equations class. So we can think of this as our b sub n. So that means our series for f of x is given by this. We've got the sum as n goes from 1 to infinity of b sub n, which is all of this. Now, initially, you might think that those are not constants, but those are actually constant values for different values of n. That times the corresponding sine function. We're going to have a sine of n pi x over L, where L is 2. And those are going to be sine functions of different frequencies. And if we wanted to, we could see that this expression, and this expression all have a 2 over n pi in common. So we could factor that out from everything. But I don't really think it makes it that much simpler, honestly. We'd have a 2 times negative 1 to the n there, minus 3 times this cosine function. And it's not actually a function, that's just a number that's either 1, negative 1, or 0. And then over here, if we took out 2 over n pi, we'd still have a 2 over n pi left times these sine expressions, which also are either 0, 1, or negative 1. Okay, and that's the sine series for this function f. Now, when you're asked what this converges to, what this series converges to on the interval from 0 to 2. Well, we know it converges to f when the periodic extension of f is continuous. So let's look at that periodic extension of f again. We're on the interval from 0 to 2, and it's continuous on the interval from 0 to 1, including 0, and it's continuous on the interval from 1 to 2, not including 1. So if I were to look at what this converges to on the interval from 0 to 2, this is what I would see. We're going to get exactly that, exactly f on the interval from 0 to 1, including the endpoints, and on the interval from 1 to 2, not including that left endpoint. Now, at x equals 1, we've got a jump discontinuity. So our limit from the left is 1, our limit from the right is negative 2. So our series will converge to the average of that 1 and negative 2. So if we add 1 and negative 2 together, and then we divide by 2, we get 1/2, or negative 1/2, excuse me. which makes sense. We're bridging half the distance from there to there. And that's what we mean when we say that the series converges to this when x naught, when x equals x naught is a jump discontinuity. Oops. So this series will converge to this function. On that interval. So let's write that down. Got x on the interval from 0 to 1. -1/2 at x equals 1. And -2 on the interval from 1 to 2.